All right. So what I'm saying is, when you have gamma-gamma correlation, you can determine the multipole order L, because there is an angular distribution. There is distribution of at different angles. What you count as gamma rays, that number is different. So that is a signature of L value of the angle, that is gamma ray. So this is helpful in determining the nuclear energy levels. That is, suppose I don't know what is the label associated with a energy level. That is, I am telling you, if this energy level has a JA, pi A, another energy level has a JB, pi B, then gamma ray carries a L value, and whether electric type or magnetic type. That's what I have told you. Now, what you have experimentally, what I find is a gamma ray, and I detect it. When I detect it in different angles, at different angles, then I do find what is called as angular distribution. This is written as gamma-gamma angular correlation. Notation is W theta 1, 2. What is the angular distribution when I do such a experimental detection? This is a signature of the L value of gamma. So I am interested in finding the L value, and through L value, I want to infer what are the energy levels, JA, pi A, JB, pi B, which means I indirectly, from a given theory, I predict what is experimentally possible. From the possible experimental studies, I turn back and say, this is the spectroscopy. These are the energy levels. I have told you, for hydrogen atom, we know the energy levels experimentally as well as theoretically. Nucleus has difficult situation. We don't know anything. Can anything give me any insight about the nuclear energy levels? One of them is electromagnetic interactions in nuclei, and it indeed tells you, you can study gamma correlate, gamma angular distribution, and predict the multipolarity. And through multipolarity, you can do nuclear spectroscopy. Now, I will tell you a specific example. You had told me in the last class that cobalt-60 emits 2 gamma rays. How is the energy level? You should know, being a nuclear physics student, you should know how the energy levels, what are the energy levels giving you 2 gamma rays. So I have a cobalt-60 nuclear level. It emits a beta particle. There is a beta particle, and then the nucleus, after the emission of beta particle, it becomes a different nucleus because beta is emitted. But I am keeping a source which is cobalt-60, and the cobalt-60 emits a beta particle, and then it is in the excited state of some other nucleus. It emits a gamma-1, and then it emits a gamma-2 to go to ground state of the daughter nucleus. Beta is emitted by cobalt-60, and the cobalt-60 itself, that is in a, when it comes here, it is in an excited state. What happens when beta particle is emitted? Will the nucleus be same? What happens to the nuclear numbers, quantum number, that is, whatever are the numbers associated with a nucleus in a beta decay? I want your answer. I will write it. Suppose I have a nucleus X. What is characterizing a nucleus? I will say there is a mass number, there is a proton number, and there is a neutron number. Mass number, atomic number, and neutron number. A is Z plus N, always. For any nucleus, A is Z plus N. Now I am telling you, this emits a beta particle. What is beta? Beta has its own numbers. That is, I say that is an electron. A electron has, what is A associated with electron?
0.
Z associated with electron?
-1.
-1. So N is 0. Okay. So that is what I have. So this should be compensated by, I say, a daughter nucleus. Forget about a neutrino. You know that neutrino gets emitted. I will write it like this. But why nucleus, other nucleus that I have, it should have a prime, Z prime, N prime. What happens to A prime? What is A prime? What is N, Z prime? What is N prime? In the decay, in the beta decay. Suppose I write it in this way. Neutron becomes a proton plus a beta particle plus antineutrino. What is the N has? What is A value of N? Mass number of N. Mass number of proton. Mass number of electron, etc. That is, I am just testing you if you understand these concepts. Okay. What is mass number? What is proton number or atomic number? What is the neutron number for a neutron? What is Z for a neutron? Am I confusing?
0.
This is 0. What is N?
1.
1. A?
1.
A should be 1. Z plus N is 1. Okay. So now I will say for a proton. Okay. For a proton, A is 1, Z is 1, N is 0. Okay. So now what happened here? A is remaining the same. Z changes by plus 1. N reduces by 0. So I will write a rule for beta decay. Z goes to Z plus 1. Whenever neutron decay happens, Z goes to Z plus 1. N goes to N minus 1. A goes to A. So now tell me what is the Y here? The daughter nucleus in any beta decay, whenever I take A, this is A prime is equal to A. Z prime is equal to Z plus 1. N prime is equal to N minus 1. So I am taking a cobalt 60, let us say. What is cobalt 60 atomic number? Can you check it? Cobalt atomic number. You can check it using your Google or your mobile, whatever. Atomic number of cobalt 60.
27.
Okay. I write 27. Neutron number, that is 60 minus 27. Correct? 33. In a decay, beta decay, I find a beta particle, fine. What should I write here? I write daughter nucleus as Y. And then this has a antineutrino, I don't care. But now what is the Y? Y should have a atomic number. What should be the atomic number? Sorry, not atomic number. What is the mass number for Y? It doesn't lose nuclear mass because electron is emitted. Nuclear mass remains the same, correct? So this should be what here? What should I write on top? Number.
60.
60 only. And here?
28.
28 and 32. So can you check what is atomic number 38 nucleus? Just to get you involved in my whatever I am doing, I am just trying to ask you so that you will know what to check. Atomic number 28. What is the
Nickel.
atom? So it is nickel. So I write nickel 60, 28, 32. This is what is obtained. But I don't write it when I explain it because our source in the laboratory is cobalt 60. I keep this source. Within no time, it decays into a beta particle. And then this nucleus, what I am showing here as a line, this is the nickel nucleus, nickel in excited state. That decays into another level. I have energy levels written because people have already done the spectroscopy. They have given the names. J pi is 4 plus, J pi is 2 plus, J pi is 0 plus. They know the values, so I am writing. But how do I do angular correlation study is what I will tell you next. So this is a gamma 1, this is a gamma 2. These have energy 1.33 MeV. The other one, gamma 1 has, okay, check it. So this is 1.332 first gamma ray. Gamma, second gamma ray. Gamma 1 is this difference, this 2.507 minus 1.33. You check it, you will get whatever value you have got for a cobalt 60 decay, which are the peaks, photo peaks of 2 gamma rays. Fine. But you don't know, what you don't know is these are cascade gamma rays. You are going to use cascade gamma decay in this particular analysis. You have cobalt 60. This decays in whatever is shown. Experimental setup for gamma-gamma correlation studies. I want to study gamma ray, second gamma ray, with respect to first gamma ray. How do I show you what is the experimental setup? I will keep a detector 1. This detector 1 is whatever you have in your laboratory. Let us say sodium iodide activated with thallium photomultiplier. And this is, I say this is a fixed detector. I fix it in one place. And then I do have a preamplifier. As usual, you have all those things in your setup in the laboratory. We don't, I'm showing block diagram of this kind of things. So it is preamplifier and then an amplifier. And then what happens? I have a single channel analyzer, but I call this as timing single channel analyzer. That is, at what time the first gamma ray comes. We used to have timing SCA earlier. That means I can also see if the other gamma ray comes a little bit delayed, will I be able to detect the 2 gamma rays in coincidence? So that is, I know to detect 1 gamma ray using a single channel analyzer or a multi-channel analyzer. That is known to me. But now what I am saying is, if I have a timing single channel analyzer, then I can detect other gamma ray coming from some other place with some delay. So what I will do now is, 1 photon is emitted. So 1 gamma ray is emitted. I detect it here. Fine. But then I have another gamma. Detector 2 detects another one. This detector 2 is movable. I will say that first detector detects. I move this detector all around the first detector so that whenever the detection is done, second gamma ray is making an angle theta 1, 2 with respect to the first gamma ray. That's the arrangement. So I keep moving the second gamma detector, and there is a again preamplifier, amplifier, timing SCA 2. Then I ask, are these two coming in coincidence? That is because it is a cascade gamma decay. Cascade means 1 gamma ray comes, following it another gamma ray comes within some short duration. So if these two come within that short duration, I get 1 count. Coincidence says I have got 1 count. What does that mean? That means in my, this is a block diagram, fine. But what I am trying to tell you is, suppose you have a gamma ray. Let me write this. So I have a gamma ray emitted and it is detected using, let us say, SCA1, timing SCA1 detects it, let us say. Then timing SCA2 is kept at some angle. This is z-axis for me. And then I will keep it at this point. I keep, let us say, TSCA2. Source is there, but time, this TSCA2, same source, it gives you gamma 2 counts. I keep timing SCA2 to tune to detection of gamma 2. That is, energy of this can be fixed. I am only detecting gamma 2. I am not detecting gamma 1 here. This is gamma 1. This is gamma 2. And gamma 2 is detected at an angle theta 1, 2, for example. And I keep moving this for every now and then. That is, I have to detect What are the number of counts at theta 1, 2? Counted for, let us say, 20 minutes. Then theta 1, 2 varies. I count the number of gamma rays for theta, change theta 1, 2, etc. When I do that, I have to make sure this gamma ray and this gamma ray, gamma 1, gamma 2, they have correlations. How do I check it? I have to check they have correlated. That means I have to count these two gamma rays, not just like that. I have to put what is called as a coincidence counter. What I have done here, I have fixed SCA1 and I have moved, that is for one angle, this is a movable thing, movable detector. So now TSCA2 is there and I do get one gamma ray here. If suppose one gamma ray comes here within such a short time, then both are detected. That means I get one click, one count is detected. That means I have both the gamma rays and I say this is because I have a gamma 1 and then I have a gamma 2 coming in this particular setting. That's what coincidence count tells me, that I have a cascade gamma decay and cascade particle 2 is making an angle theta 1. That is the kind of setup that I have. With that, I will now say, fine, I have all this arrangement ensuring that gamma 1 and gamma 2 are in coincidence and they are detected. Having said that, I will say fixed detector, okay, this is English again. Fixed detector is set to measure gamma 1 only, which means I have photopeak energy fixed. I only detect gamma 1. Photopeak energy can be fixed by fixing the LLD ULD in your gamma ray detector. So only the movable detector is set to receive gamma 2 only. That is, its energy is tuned to gamma 2 value. The movable detector is placed at different angles theta 1, 2. Coincidence counts are registered as a function of theta 1, 2. The measured angular correlation function is then compared with the theoretical correlation function W12, and it is given by, for example, cobalt 60 experiment gives you a W12, which is A0 plus A2 cos square theta 12, A4 cos to the power 4 theta 12. I don't know what are these coefficients, but theoretically you can calculate them. If I plot experimental data of W12, what is a W12? It is the number of counts at different theta 12 values. At different angles theta 12, you will find different counts. So that plot will reveal that it is actually it is kind of a function which is given like this. That is, this is theoretical. What I am showing you is theoretical. I can calculate theoretical angular correlation function. How? I had shown you for a dipole correlated. That means I have, suppose I take a, this is, let us say 0 plus 1 minus 0 plus, then I said this gamma ray is E1. This is also E1. There can be different energies. Electric dipole type, W theta 12 for the gamma ray. This shows an angular correlation that is proportional to 1 plus cos square theta 12 is what I showed. That's all. That is what I had discussed in the last class. But now I am telling you, if it is what is known as our cobalt 60, what is the cobalt 60 angular correlation, angular, that is spectroscopy? That is, this has 0 plus, 2 plus, and 4 plus. These are the energy levels. With that, it's not 0, 1, 0 like earlier. This, for this also, I can sit and calculate what is the theoretical correlation function. Having done what is the theoretical correlation function, I will now say, fine, I have coincidence counts and I counted values. This is number of gamma rays, of gamma 2 rays, which are detected at different theta 12 values. Angles are 100, 120, 140, etc. You plot it and fit it with whatever is the experiment theoretical value. You will determine what is A0, A2, and A4. So one that is this data can be fitted to that. So I find experimental angular correlation, and it is found that for W theta 1 2, 4 plus 2 plus 0 plus, I find 1 plus 0.10 cos squared theta 1 2 plus 0.0091 P4 cos theta 1 2. These are Legendre polynomials. That is what I find in experiments. P12 is cos squared, P4 is cos to the power 4. So I am writing this is what matches with the experimental data. And how do I know that this kind of a angular correlation function comes when I have 4 plus 2 plus 0 plus? That is only for this I can fit this data. So I will say the spectroscopy is 4 plus 2 plus 0, 2 plus and 0 plus. I hope you understand what I am trying to tell you here. I have done only what is called as there is a cobalt 60 source. This cobalt 60 source, I have this decays, this is the energy level, this decays into some other nucleus emitting a beta particle. And this goes to other level, which is, let us say, some level, and then one more level. There is a gamma 1, there is a gamma 2. And this gamma 1 has some energy, dipole moment, and all that. I calculate what is the W theta 1 2 for JA going to JB, going to JC. That is, this is JA, this is JB, this is JC, let us say. If I do that, I will find when JA is equal to 4, JB is equal to 2, and JC is equal to 0, I get a correlation coefficient A0 is equal to some value. A1 is, let us say, 0.0 something. A2 is equal to I think whatever I have shown you here. This is a typical value, 1.102, and A4 is 0.0091, etc. If you take these values, I do have associated. This is experimental. And I will associate with theoretical values, which is 4, 0, 4, 2, and 0. That means I can determine from my experimental angular correlation, this angular correlation studies, I will be able to label JA as 4, JB as 2, JC as 0. That is spectroscopy. That is what I learned. From that, I have to now find why 0 to 4 comes. That is another analysis. But at least I have some little understanding about nuclear energy levels. Is that fine? So next semester, you will have an analysis experiment where we give you data of angular correlation, and you will have to find out cobalt 60 and some other nucleus, what is the angular correlation that is plotted, whatever is given to you from that data, you have to decide what are the gamma rays emitted, what are the multiple values, and associated energy level labeling. That is kept in the next semester for your experiment. That is analysis experiment is there. So you have to remember this. So that is a part of angular distribution and angular correlation studies. So what all I have covered in gamma decay now, let me just tell you so that we are in tune with what is being done. So let me say, I told you about selection rules. These selection rules introduced what is multipolarity, what is associated electric type, and magnetic type radiations. That is fine. So then I told you these things with, I told you L is not equal to 0 and kind of things. So then we did a detailed mathematical analysis of electromagnetic multipole expansion multipole expansion of electromagnetic radiation. That is solution of the Maxwell field in the source-free region, source-free definite energy, given source-free definite energy radiation. What are the solutions of the Maxwell equation? That gave me L and electric type and magnetic type. All those things came in this analysis. Then we did what is source dependence of any electric type or magnetic type radiation. Source dependence of multipole values, multipole radiation. So that is, what is the amplitude? What is the transition for this? So this we did for both classical and extension to quantum probability, quantum theory, where if the energy levels or wave functions are known, you can determine what is the quantum transition probability and say how this depends on the source. The source dependence comes in terms of what are called as QLM, MLM, which are quadrupole, what are known as multipole moments. Multipole moments of distribution source, or a source dependence is in terms of multipole moments. I told you multipole moments are nothing but dipole moment, electric dipole moment, magnetic dipole moment. They are all dependent on what is our charge distribution, and my radiation, whatever is the transition probability of finding a radiation with a particular L value, multipole value, it depends on what is, whether the source has a multipole moment of order L. So how it depends explicitly can be given by the amplitudes which depend on the multipole moments. I have already just shown you these things, and then I was talking about how to determining the multipole value of a radiation experimentally. So this is experimental. In this experimental study, I brief you, you have an angular distribution in general, intrinsically, for a particular multipole gamma ray. But that angular distribution cannot be seen because our source is incoherent. Once we emit, it emits a gamma ray in one particular direction, other time it emits in different direction. So you don't have overall, there is no M dependence, it is incoherent. There is no M dependence means angular distribution gets washed out. Then I told you there is a gamma correlation study which retrieves back. It tells you how to determine the L value. So from that you can determine what is nuclear energy levels or nuclear spectroscopy is enabled. So all that I have told you in this sequence, it is only up to some extent you can follow very well. That is, and many large extent you have to connect it by what you know already, little bit, little by little. No problems explicitly, but angular distribution given a ZLM, find for a L is equal to 1, L is equal to 2. What is the angular distribution? How would it look like? Kind of ideas should be there. With this, I am left in the gamma decay part. What I am left with is it possible? We don't know nuclear wave functions. When I don't know nuclear wave functions, is it possible for me to determine, estimate the value of, say, let us say AELM mod squared, AMLM mod squared, theoretical estimate. That is, by doing whatever we can do, is it possible for us when we don't know explicit structure of nuclear wave functions? I don't know it. If I don't know it, can I estimate it? At least, can I estimate it? Yes, this is possible. These are what are known as Weisskopf estimates. Weisskopf is one of the scientists who was very well known for nuclear gamma decay part. So he developed it. So estimates. So I do this part by showing you how he calculated various, that is what is the amplitude, why L is equal to 1, L is equal to 2, how it is going to change when you have different, when you don't know anything about the nucleus, still can you calculate what are the probabilities of one gamma ray coming with L value, M value is more dominant than the other gamma ray emitted in the same nucleus with some other multiple values. So then what I am left with further is what is called as internal conversion. Internal conversion is another process in a nucleus where electrons are emitted. These two are the last bits of our gamma decay. So after that, I will shift to particle physics. By that time, we are well equipped with certain understanding of particle physics. So I will stop it here because these are more detailed. Vyskov estimates are little more, it involves much more detailed thinking. You have to have a fresh mind, then you will understand what I am telling you about Vyskov estimates. And internal conversion is another chapter on how nucleus interacts. Nucleus interacts with electromagnetic field, let us say. It is nucleus is in an excited state. It comes to lower state, but it doesn't emit no gamma decay. If it is not gamma decay, there is another process which is possible, another process which makes a nucleus to come down to ground, another level, by emitting, by giving its energy to one of the electrons. So that is a theory where I will again indicate how you determine what is the difference between internal conversion probability and what is the gamma decay probability. These two are competing. Which is better, which will be seen in a given situation. That kind of analysis will be done in internal conversion. So these two things I will do in next class. When is my next class? I will check it and keep myself ready. But this Thursday and Friday, we don't have classes because we have our admission process here. Don't come near the department. There will be huge number of people. M.Sc first year admissions are going to happen. You have to attend your classes or stay at home. Don't move around. That's why we are doing online classes. If you have any urgent, emergency thing, message, depending on your question, how important it is, I can respond. If I am too busy, I will not be able to respond. So have some amount of, understand what I am saying, because we have too much of work as far as admissions, NAC preparation, that is under concern. So I just like to teach with whatever I know, whenever it is possible. But this week on Friday, I will not be able to take your class. So I will see when I can engage my general class next. So special class, I don't know when I have. Do you have the timetable? I will check it, 1 minute. No. All right, I will stop sharing. If you have any questions, that is what I have told you today is an experimental setup. So you should be able to